Push that rock with Simpson Math. Let's talk about factorial. Factorial is a mathematical operation, and for us it's just on whole numbers. So you take a whole number like this, and the symbol for factorial is an exclamation point. So we read this 5 factorial, and it means multiply 5 by every whole number before it until you get to 1 where you stop. So if you'll notice, that means that this 4 times 3 times 2 times 1 is 4 factorial. So each factorial, like 5, is the same as 5 times the factorial of the number before it. Now 4 factorial is 4 times 3, which is 12, times 2, which is 24, times 1. So 24, and 5 times 4 factorial then is 120. So that's what 5 factorial. Now there's a special definition for 0 because it's a whole number. And notice we stop at 1. So 0 doesn't really fit into this definition. It has its own definition. 0 factorial is always 1. Okay? So there's factorials for you. It's pretty easy to understand, so I think that's enough examples. Now, for the problem I'm going to do in this video, we also have to deal with this number. Ln stands for natural log. I know that's out of order, but remember that in the Romance languages like Latin, they sometimes put the adjective after the noun. So anyway, in the derivation of the symbol, we use Ln for natural log. Log is an operator. It operates on a number and produces a number, okay? And we're going to learn more about it in a couple of weeks, and you've probably studied it some in Algebra 2. But for right now, this is just think of this as a symbol for a special number or a strange number. We'll call it S for strange. The definition is that if you take Euler's number and raise it to this strange number, you get 2. That's the definition of S, which I'm using S to represent the natural log of 2. So E, which is Euler's number, raised to the natural log of 2 equals 2. So, it's a very strange definition. It's, but just think of it as a special number, and all we need is its approximation. So we'll write down its approximation. And I don't know it exactly. If you type it into a calculator using your natural log key, it'll give you something close to, let's see, I don't have it memorized out to very many places. So I don't know what comes after this. Maybe a 7, and then I don't know, 2 maybe. I don't know, but so anyway, notice it's very close to 0.7. It's slightly less than 0.7, which is 7/10, okay? So this special number, just think of it as a number super close, but slightly less than 7/10 for purposes of this video. And we'll understand numbers like this more in a couple of weeks. Okay. So why did I need this strange number in this factorial thing? Well, we have here an expression, a definition of b to the x. This is a function based on some number b, and we want to find it. I gave y'all a similar one that doesn't have this. It has factorials, but doesn't have this very strange number up here. So yours will be a lot easier to do. You don't have this strange number here, but I left myself the more difficult one and left y'all the easier one. I left y'all then what mathematicians would say is the natural base, but I'm dealing with a less natural base, I guess. I don't know, it's typical base, but anyway, this base raised to this x, so an exponential function here, because the variable is in the exponent, is defined as an infinitely long, this ellipsis here means it goes on and on and on, an infinitely long polynomial. And the x to the first, x to the second, x to the third, x to the fourth, x to the fifth, and so on. And the coefficients follow a pattern. The natural log of 2 over 1 factorial. The natural log of 2 to the second power over 2 factorial. So notice the powers are matching the factorials. 3x to the third, natural log 2 to the third over 3 factorial, and that's the pattern. And what we want to do is compute b, to find out what b is. So our goal is to discover b. What is b? If this is the definition of the exponential function with base b, what is b? Well, then we want to know b to the 1, because b to the 1 is b. So that means our x is going to be 1. So the very first step we're going to do, if we want to know b, is put in 1 for the x's. So I have 1 plus, I put a 1 here, a 1 here, a 1 here, a 1 here, a 1 here. Well, if you put 1 times something, it's just the something. So I have just natural log of 2 over 1 factorial. 1 factorial is just 1, because that's where you stop, is at 1. Then I have the natural log of 2 squared, because 1 squared is still 1, so this doesn't change, over 2 factorial, which is 2 times 1. Then I have the natural log of 2 cubed over 3 factorial, which is 3 times 2 times 1, times 1 to the third, which just leaves it alone. Natural log of 2 to the fourth over 4 factorial is 24, and natural log to the 2 to the fifth over 5 factorial is 120. We did that on the other page. And it keeps going. The next one would be natural log to the 2 to the 6th times 1 to the 6th, but 1 to the 6th just becomes 1, over 6 times 120, and so forth and so forth and so on. Now notice, remember this was a fraction. The natural log of 2 was about 0.6931472-ish. So when I raise it to the 6th power, it becomes really small. And then I'm going to divide it by this really large number here. So it's going to be super small. So if we're going to estimate, remember we estimated series before. If we're going to estimate this series, we can just add up these first few terms, because these terms are getting so small. Now it's a little dangerous. There are an infinite number of them. So these infinite number of small numbers could add up to a significant amount. But this is getting so tiny that I think we can safely say that if we just add up these terms, we'll have a good estimate. And it turns out that is the case. Just adding up this many terms, I'll have a good estimate for this. Now, if I had a higher power of x, I might have to go out way further. Like if I needed to know b to the 4th, I might have to go out a lot more terms. Or maybe not. Maybe I go fewer if this is these, because oh no, because we'd be putting in 4 to the 2, which would be 16. Yeah, this would become so much bigger. And 4 to the 3, this would be some. So I'd have to go out way more terms in order to get a good estimate. But since we're only putting in 1 for x, I think this is enough terms. So I'm just going to add up. I'm going to treat these as negligible out here and just add up these. Now, to do that, I'm going to remember that the natural log of 2 is slightly less than 7/10. So I'm going to treat this as 7/10. Okay? Now, that's bigger than what it really should be. So I'm making this bigger. So that means that b to the 1 is smaller than what I'm doing now, because I just made, by changing natural log of 2 to 7/10, which is a little bit bigger, I made the right hand side a little bigger. So here I have 7/10 squared over 2 plus 7/10 cubed over 6 plus 7/10 to the 4th over 24 plus 7/10 to the 5th over 120. And it goes on and on and on, but I'm just going to deal with these numbers. So that's another reason why b is less than all of this, is because I would also add in all these small, tiny, admittedly very tiny bits, but these tiny numbers out here would also make this side bigger. So Anyway, we're going to use just these numbers as our estimate. Now, I need a common denominator, clearly. You know, the 120 looks like a pretty good denominator. You know what? I think I might could just add these. This is getting a little crazy with the 120. It's like 7/10 of the fifth is really small. You know what? I'm going to even just throw this one out. I mean, this is negligible as well. I can't spell. You know, it's like 7/10 of the fifth is tiny, and then you divide it by 120. So let's just add these, and I think we'll get a pretty good estimate. So we're going to get a common denominator. See, it's going to be 24 over 24 for 1. If I'm going to give this a common denominator 24, then I have to multiply the top by 24. And so I have 24 times 7/10 plus, 2 goes into 24 12 times. So I have 12 times 49 over 100 over 24. Plus 6 goes into 24 4 times. So I have 4 times. Whoa, wow, we need the powers of 7. Let's see, the powers of 7. Let's see, there's 7, 49. The next one's going to be 343. If I multiply 49 by 7, I get this. Multiply 343 by 7, we're going to get 2,401. So those are the powers. So then this one, the third power is 343 over 1,000 here. Plus, now 24 already has the common denominator, so we can just call that 2401 over 10,000, because 10 to the fourth is 10,000. Wow. Man, I better get out another sheet of paper because I'm starting to write so small, and I do remember a comment that said they couldn't see. So let's say what we have so far. So we have b to the 1, which is just b, is slightly less than. Let's add them all up. They're all over 24 because the common denominator is 24. And it's 24 plus 24 times 7/10 plus 12 times 49 over 100 plus 4 times 343 over 1,000 plus 2401 over 10,000. Wow. Man, that's a lot. Now, hopefully we can all see this. It's in the video, and it's bigger now, so easier to see. So what are we going to do next? Well, we're going to have to, simplify these terms right here. This one's tiny. Look at that. I mean, that's you divide 2401 by 10,000, and you're just left with 0.2401. So 4 times 343, let's get some scratch paper out and figure out what that is. 343 times 4, 4 times 3 is 12, carry 1, 4 times 4 is 16, and 1 is 17. 4 times 3 is 12 plus 1 is 13. So that's 1372 over 1,000. So that's 1.372. Plus, we need 12 times 49. So we'll turn to our scratch paper again. Well, 12 times 49 is not quite as hard as you think. 12 times 49 is really just 12 times 50 minus 1. So 12 times 50, well, that's going to be 600 minus 12. 12 times 50 is 600. 12 times 1 is 12. So we get 588. So we have 588 divided by 100, so that's 5.88. And then 24 times 7, well, 7 times 2 is 120, and 7 times 4 is 28. So that's 168, but it's divided by 10, so that's 16.8. And then we have this 24 here. And it's all over 24. Now I'm just going to add these up, and I'm going to, just on some scratch paper, add those up, and just stack them very neatly. and then, just place value that out. And looking that, I can see that I'm going to get 48.2921 over 24. Well, 24 goes into 48 2 times. So we have 2 and just a tiny bit. So B is less than 2 and a tiny bit. I mean, it's the remainder is, 24 doesn't go into 2 and 24 goes into 29. So it's 2.01. And then the remainder from 24 and 29 is 5. And 24 goes into that 2 times with the remainder of 4 and goes into 41 less than 2 times. So 1. So our base is less than 2.0121. Now we had all those infinite number of terms, but I think they're just going to change the value out here. So it's less than 2. Now remember, we overestimated the natural log of 2. Remember that? We overestimated the natural log of 2. So a natural guess for the value of B might be 2. And it turns out that is the true value. It is 2. Okay? Now, that routine that I just went through, you're going to have to too. Now, what's the takeaway from this? I mean, that seemed awfully magical that I settled on 2, but that was because I did this overestimate thing. And if you had a computer to help you get the limit of this infinite polynomial, and you didn't have to round off to 7/10 when it was really 0.693147, it actually goes out, forever, then it would be 2. And so what's the takeaway? Well, we saw what was that definition of 2 to the x. The true definition for 2 to the x is 1 plus the natural log of 2 over 1 factorial x plus the natural log of 2 being squared over 2 factorial x squared plus the natural log of 2 cubed over 3 factorial x cubed, and so forth and so on forever. And why is this a better definition than the one we had before? Well, remember before, we couldn't handle inputs that weren't irrational numbers. If they weren't rational, we didn't have a definition. So if it's a whole number like 2 cubed, well, that just means multiply it 3 times. If it's a integer like that's negative, like -3, well, that just means multiply the reciprocal 3 times. Okay. If it was a fraction like 3/2, well, that just meant multiply the square root. Because of this 2, it's the square root of 2 3 times. Okay. So another example of that is, what if I had 4/3? Well, then that means multiply the cubed root of 2. Because of this 3, it's the cubed root of 2. And how many times do I multiply the cubed root of 2? Well, I do it 4 times. So we have definitions as long as the exponent is a rational number. But we do not have a definition for something like 2 to the square root of 2. We don't know what that means. Well, we do now. It means you put in square root of 2 for all the x's, and you simplify this. Now, obviously, this looks like a lot of work. You say, but that's a lot of work. Well, yes, it is. And in an advanced class, you'd learn how to be able to compute that. Okay, or you write a computer program to compute it for you. But here's the reason why this is so powerful. It turns out that if you use this definition, then not only can you include the square root of 2 in your as an input into the function, but the square root of 2 turns out to be exactly what you think it would be. It's somewhere in between 2 to the 1.4, because square root of 2 is slightly bigger than 1.4, and 2 to the 1.42, because square root of 2 is slightly smaller than 1.42. So it turns out to be the exact value you need to be. Not only that, but all of your exponent rules still apply. If I have the square root of 2 to the square root of 2 times 2 to, say, 4, I can still use my rule that like basis is 2 to the square root of 2 plus 4. And if I put this into this definition and this into this definition and multiply them together, I'll get the same thing as if I put in square root of 2 plus 4 into the definition. And so it works. All of our exponent rules still work even for irrational inputs. And the definition turns out to be exactly so. And mathematicians are always looking for consistency like this. And they found it with these infinite long polynomials. They're actually called Taylor series. Remember, when you add up the terms of a sequence, it's called a series. And this type of series is actually called a Taylor series. And it's studied in Calculus 2 or Calculus 3, depending on the curriculum. But somewhere in the calculus sequence, you come across these. And right now, I just want you to be able to do what I did and evaluate one. Math made simple. It's Simpson Math.